Thank you so much. Thank you for the introduction. I hope that you can see my screen. Let me just say a few words about who I am. My name is Amy, and I am at Örebro University. I'm affiliated with the Center for Applied Autonomous Sensor Systems, which is the center at the university that is responsible for doing research within both AI and autonomous systems. The center has a focus on perceptual and cognitive abilities of autonomous systems. So we look at AI, we look at robotics, but in particular, we look at the intersection between the two. And we have 5 different subgroups or labs, and I'm leading one of the labs, which is called the Machine Perception and Interaction Lab. And it's the center which is part of WASP AI. A quick word about the Machine Perception and Interaction Lab. So we do a number of different things. We pursue a number of different research directions. We're about 20 people in the group, looking at, in particular, how we can make sense out of sensor data and extract meaningful information from sensor data. Often where this data is emerging from complex physical systems, they can be robots, but they can also be distributed sensor networks. And we really want to follow and pursue the whole chain. So go from the extraction of this information to facilitating good interactions between humans and robots and humans and different systems. And when I was asked whether or not I could give a talk, and the theme of the conference is on virtual worlds, I saw that this was a very good opportunity to lift one of the directions that we've been pursuing within the lab, which is particularly focused on telepresence and teleoperation. And telepresence and teleoperation, as I'll explain in the next few slides, creates a very interesting setting for interaction, because in these cases, you have the robot which is acting as an embodiment of a human operator. So it's not necessarily studying the interaction when the robot and the human is external to the robot, but also when the human is part of the robot. And that creates a number of very interesting research questions that we want to pursue. So what I'd like to do in my talk is just to tell you how we're working with virtual worlds in telepresence, how we work with them in teleoperation, and if time allows, maybe also lift what we are doing in these other directions that are not necessarily only human systems interaction, but other directions that are more related to semantic perception. So let's talk a little bit about telepresence. So there's a particular class of robots called mobile telepresence systems, and these are remote controlled wheeled devices. And the important thing to remember when it comes to these MRP systems, as we call them, mobile robot presence systems, is that the focus is on social interaction between humans. That's the main objective. And another way of talking about these systems is really just calling them, as we call them, Skype on wheels. They're really quite simplistic systems. I think the majority of us have seen them. The type of platform that we've had the most experience with for the past few years now is the one called the Giraffe, which is this blue telepresence robot, where we've worked together with the company to help develop and evolve the robot. And what we found when we were first introduced to these types of platforms was, first of all, they're very simple platforms, right? And maybe for us, we were a little bit maybe not so enthusiastic to working with these types of platforms because they have very little sort of sensing modalities. But after a while, looking at how interaction was taking place, what we did find was that there were a number of challenges that were emerging that we could see in the interaction between humans when they were using these MRP systems. Like, for example, these systems have a high cognitive workload for the operators. They're intended for many novice users, which have, of course, maybe some difficulties in operating these, so driving the robot while socially interacting. There are limited sensing abilities, which can, of course, create an additional burden on the operators. There can be artifacts in the environment. There can be contextual information that is missed. So what we wanted to do is we wanted to ask ourselves, Well, what methods are available to characterize and measure the quality of interaction, and also what methods can be used to automatically and dynamically improve upon the quality of interaction when we are using these robots. And this is, I think, the part where virtual worlds come in. And although we never really explicitly talk about virtual worlds, they're there. So if we look at the first part, which is to develop methods to characterize the quality of interaction, there are several methods in HRI that you can use. Proxemics is one that many who are working within HRI know, which is basically understanding the distance and the physical behavior between the human and the robot. But there's also another theory that is quite useful in this context, which is the theory of F formations. So F formations is how we humans orient ourselves when we are in an interaction. And this is a well-studied theory coming out of psychology. It was coined in around the 70s. Maybe you can tell by the clothes that those people are wearing in the image up there. That says that depending on the task and the context, we tend to orient ourselves slightly differently. So when we're in a situation, and we might know it when one person is in focus, that everyone is oriented towards that person. Or maybe you recognize a situation when you're on a dance floor and everyone is equal, you tend to orient yourselves in a circle. And what we wanted to know was whether or not, when teleoperating these types of platforms, are operators adhering to these F formations? And we did a lot of studies where we looked at how operators would use the telepresence robot. So in this film, it's the white device, and how they orient themselves to the users. And what we found was that operators were not always adhering to F formations when they should. And we also found that there was a strong correlation between the operators who appreciated the system and those who used F formations. So when operators relied on F formations, they appreciated the system more. It was always consistently rated as being better. So what we wanted to do is explore this aspect a little bit further. So instead of doing these experiments in a real lab situation, what we did is we created a virtual environment to study a bit more how people are interacting in these kinds of situations. And so what we did is we used a number of virtual agents, and then we explored how operators were teleoperating the robot using the exact same interface they would otherwise have for a real robot, and then studying how they're placing themselves into these F formations. And then we did retrospective interviews to see whether or not operators thought that they were in fact operating and placing the robot where they had intended to. And what we found was that there was this dichotomy in these telepresence systems, so that the factors which led to good navigation actually contradicted to factors which led to good social interaction. So the next question that we wanted to explore was whether or not we could do something about this. And what we saw was that here we can use virtual worlds again, or actually tools coming from virtual worlds, and overlay them onto reality in order to assist operators in getting a better understanding of how they should drive and operate in the environment. We did this when they were navigating and introducing features for semi-autonomy and sliding autonomy, where, for example, certain functionalities that allowed for slowing down the robot or even turning the robot away from obstacles as operators approaches obstacles could occur. But we also looked at this idea of F formations and assisted operators in finding the best spot for which they can join a social group. So in the picture here below, you see that there are two people. They're wearing these funny helmets because we have a mocap system just to do the verification of a ground truth. But from the perspective of the robot is actually giving a suggestion to the telepresence operator of where they can place themselves when they want to enter that particular group. And we are now looking, given that we are in this pandemic situation, how we can continue to explore our MRP systems. And one of the the works that some people from the lab are exploring is creating a modular platform of off-the-shelf components where you can easily build your own telepresence robot. And we're interested in this case, not only on the social interaction as I showed you before, but this time we're attaching UV lamps to the telepresence robot and looking at whether or not these robots can be used for disinfection. And here, what we want to do is detect and show, for example, surfaces that can be disinfected. And again, using this adjustable autonomy to bring operators into the loop in a good way. Let me move on to teleoperation because we worked quite a bit in telepresence, but we're also interested in teleoperation. And actually, a lot of the work that we did here was motivated by the fact that we have some collaborations with some companies that are doing 3D printing. And these companies that are doing 3D printing, if you're printing in metal, you have to clean out the printer, and these have very sort of dangerous powders, and you don't want to have a human in that environment at all. And they approached us and asked us if we could automate this solution entirely. And we said, well, this is quite difficult, but maybe we can bring the operator into the loop. And so we started looking at different research questions of how we can facilitate a good interaction for the purpose of teleoperation. So here there's a physical interaction, and it's not only the social interaction as in the previous case. And here what we've been looking at is we've been looking at ways in which we can bring in what we call interaction proxies to control or to remotely control the robot. And here the virtual reality interface provides the operator with immersive visual feedback. And one of the things we're trying to look at is also how we can measure, again, the workload and the performance on the operator in order to provide the best interaction scenario as possible. And this year we've had quite a number of results in this particular direction. And again, looking at adjustable levels of autonomy in which the operator can focus on only certain high-level tasks, such as isolating the robot's position, whereas the robot then autonomously regulates its orientation. And we have one of our researchers who's also looking at the possibility of bringing in multiple robots where there is only one single operator. And then the question is how to map between the haptic device that operator is using to be able to do a multi-robot teleoperation situation. So I have a few minutes left, and I lifted as much as I could, both the virtual worlds in telepresence and teleoperation. But I just want to say a very quick word about virtual worlds in the other research directions that we're exploring. I think we'll talk more about this certainly in the panel discussion and also in the afternoon sessions. But we have also some work in the lab that is focusing not so much on telepresence and teleoperation, but still focusing on how you get semantic or symbolic representations of the world based on sort of perception. And one of the things that we see is that by semantic representations, we improve interaction, but we also can, for example, facilitate the use of other symbolic methods within AI, like, for example, using planning methods. And a very important aspect in this is to look at the language grounding problem. That is, how do you connect language to something other than symbols? So how do we, for example, go from instructions, like the one you see here, remove the green big sphere, to an actual action? And many of us are aware of what's been happening in the field of visual query answering. We wanted to take that one step further and look at instruction. So visual query answering, you can ask questions, for example, what is the object to the left of the red circle? And you'll get an answer. We wanted to look at instruction where we're trying to ground actions. So if you want to remove an object or add an object. And what we've been doing here, and I just want to focus a little bit because I'm running a bit short on time, but what we've been doing here is we've been really trying to use this notion of virtual worlds into our research, partly to train these systems. So training these systems on different types of scenarios where we are able to, for example, send in a instruction, remove, for example, a blue rectangular object, and we then generate the result of that instruction. Then what we've also looked at is the possibility to port that into a scenario where we have real objects. So this is coming from our RGBD sensor, and then looking at whether or not our system has learned or grounded those actions like remove and add. And one way that we can verify that would be to have a robot, for example, that will actually follow the instructions. But another way is, again, to mix the virtual with the real. So in these images here at the bottom, what we've done is when we have an action that we've given, or an instruction, sorry, that we've given, move the red small cube to the left of the red big sphere. This is coming from the real data from the sensor, but this bottom image here, and I hope that you see my pointer, is actually a generated image. So that red cube is actually an artificially generated red cube. And the result of this is that it allows us, to some extent, to verify whether or not our grounding has been successful. Now, that was a little bit of a parenthesis, as the main focus of my talk was on teleoperation and telepresence, but I just wanted to lift up the fact that we're seeing more and more virtual worlds coming into more of our research directions. And it's interesting to see that red thread through these directions. And in general, we see that in HRI, it allows us to create good experimental environments, improve human-robot interaction and collaboration, but also more generally, there is this kind of sustainability between AI and virtual worlds. And I mean sustainability in the real sense of the world, where these two fields are really sort of feeding into each other. We showed just briefly how we can use it to explicitate the results for validation, creating or generating artificial scenarios. And I'm sure we'll talk later today in the panel also about the importance of generating training data. That was my presentation. Thank you very much for your attention.
Thank you so much, Amy, for a very nice presentation. I have a couple of questions here. Let's see. I'll choose one. From Volker Krüger, the querying answering system are really cool indeed, but they are usually based on LST and CNNs and thus not explainable. Do you think it is a good idea to control a potentially dangerous robot based on these QA systems?
Yeah, and this is a really good question. This is one of the reasons why we verify our results. You could see it in two ways. It's not just about explainability, but also about explicability, transparency. And by showing in that kind of virtual scenario where I showed that the result of the instruction, move the red block to, let's say, the right of the blue square, where we can actually show how the robot will envision the result of that action. That is one way to kind of make the system a bit more transparent. But I would agree with you, it's certainly not explainable. It's just adding a little bit of transparency. Then I would also say you don't solve the problem with the fact that maybe the robot, even though it knows what the end goal is, maybe getting there, it will create a lot of damage. So we haven't addressed that issue yet, but that I think is certainly something for others to take a look at. I think we've just tried to make one step in that direction.